Hello everyone. In the previous videos, we have already learned the definition of machine learning algorithms, classification of machine learning algorithms, as well as many important methods of machine learning and some common machine learning algorithms. So, as the last section of this chapter, we will delve into a real case to understand in detail, when we encounter a practical problem, how do we use a machine learning algorithm to solve a problem in our real life? So, in this case it is done with a very classic dataset. This is about the sale of houses in a certain city. Housing price dataset. There are 21,613 sets of housing, with living area and prices here. We can see the list on the left side. It is the area of the house and its residential price. So we all know this is a very simple dataset. It has only one dimension of features. This is the dimension of the house area that we marked as X. Then we take Y as the label of the dataset. Then we can also clearly see this price tag. It is a continuous tag. It is not a classification task. It is a continuous value. We are working on a regression task. Let's take a look. Facing such a case, we use the area of the house to predict the price of the house. What should we do? First of all, we need to analyze the problem. The amount of data in this case is very large, over 20,000 data. So there is one-dimensional feature. One of its tags is also a continuous value. At this time we can use regression, because it is a prediction of a continuous value, so we use regression algorithms to solve this problem. Here we used a simple regression algorithm. It is the linear regression algorithm. So our goal is to construct a linear regression function, and because it has only one-dimensional feature input, so what we need to build is a univariate linear regression function. That is the formula listed on the right side of our entire film. Linear regression function, here is 1U1. I believe everyone is familiar with this formula. Next, we are going to use our data to fit the final function we want to obtain. So let's recall when we first start talking about machine learning algorithms. We talked about what kind of machine learning algorithms are needed. So do we need to find this pattern from the dataset? This rule can help us solve new problems. That is to say, when a new house's area is here, when a new house area is input until we find that pattern. When you find that model, we need to have a corresponding output for its price. So our thinking is very clear now. Confirm the algorithm we are going to use. So we need to use a dataset to train that optimal algorithm, the best model to complete our entire project. Now let's take a look at one of the objectives of linear regression. Linear regression, when we are explaining this algorithm, we have mentioned that linear regression is actually about finding a straight line, and this straight line can fit the best distribution of all features of the dataset. It is to find the best straight line, like this. So, the graph on the left describes a distribution of all areas and prices. So how do we find this straight line? In this graph on the right, we can see that many straight lines are drawn. There are all kinds of them, right? But there is only one best straight line. It's this deep yellow one. Right? We are looking for the best straight line, like this, because only this straight line is the most fitting distribution for the entire dataset. Other straight lines, the data you predicted does not fit the distribution of our entire dataset very well. So in this equation, we need to find the best values for these two parameters, W0 and W1. We also need to learn how to generate these two parameters. So learning the optimal values of these two parameters is what we ultimately aim to find, the optimal model. Okay, let's take a look at how we can learn it. Learn those two parameters. So we need to find these two parameters. We need to build the loss function. What is the loss function like? The picture on the left. I believe that everyone can have a clear understanding of course. This graph is not made up of actual data from the dataset we just worked with. We used some other simulated data in a straight line here to present it more clearly to everyone. How is this loss function constructed? For example, green dots represent data. So this line in the middle is the one we want to fit. Suppose it is the final straight line. Then all errors are added together. All these errors added up are our loss function. Everyone can take a moment to think about it. If this line is over here, will its error be very large? Such a large error is definitely not what we want. The parameter we want when the error reaches its minimum value, this black line that we are drawing now, only when the error reaches the minimum, it is the line we want. It's the way this mathematical formula is listed on the right side. This formula, it's the formula of the loss function. So our goal is to minimize this loss function. Simultaneously find the subU to minimize this loss function. We have achieved our goal. Okay, so which algorithm to use? I believe by now everyone knows, using the gradient descent algorithm, by continuously iterating, so find the minimum value of this function. It's the B point on our graph here. Found it. We have found those two values, doublet, U0 and W1, that we ultimately want to find. At the beginning, how should we start this iterative algorithm of ours? Very simple. We assume point A is the starting point. It is a position obtained by random initialization. Like this. Random, any position. Is it possible that what you call random is actually over here? It could be either way here. This point is just the position we randomly initialized. But next we are going to use the AB connection. In other words, continuously iterate and optimize in the direction of the negative gradient step by step. Iterative optimization continues until reaching the final point, B global minimum value. At this point we can determine the final values of our W0. The iterative process here, we will use 3 diagrams to give everyone a presentation, for the convenience of everyone's understanding. So starting from the first image, at the beginning we can see that this is completely random. This is how our data is arranged, but at the beginning when we started at that point, its data does not match this straight line at all, completely mismatched, so that's the starting point. It is completely random, but with the iteration of our iteration, everyone can notice that this straight line is constantly approaching this data. When iterating to the final step, everyone can discover this straight line has already fitted our data distribution. This is an example of the iteration process. Everyone doesn't need to get caught up in this. How did I start? Is it too random? Will it not fit into that issue? No need to worry about this. As long as we iterate, it's okay. The learning rate and hyperparameters we set are okay. We will eventually find our best parameter. After finding this model, we need to debug and apply it. After training, be sure to conduct tests to ensure its generalization ability. This is very important. Like the housing price dataset we just discussed, here we have obtained the final result of the model. Here on the right, we list the formula. So, if we talk about your model, finally you can see the occurrence of overfitting in this case. You can add an L1 regularization, turn it into a lasso regression, or L2 regularization becomes a ridge regression. Resolve this overfitting issue. After all, regularization can solve this problem. If your model is underfitting, we usually recommend everyone to switch to a more complex model. Switch to a more complex model. For example, a model like GBDT, of course, in data cleaning and feature engineering. The application on real datasets is very important. If you find that many models have been changed, if adding a lot of regularization techniques still does not solve the issue, it is recommended that everyone continue to improve the model. Data cleaning and feature engineering construction. Some of these ways. Up to this point, we have completed the study of all the content in our second chapter. In this chapter, mainly introduced the definition of machine learning classification and some key issues to address. In the end, we also used a case study, solved a practical problem, demonstrated some processes of the entire machine learning. After everyone has finished learning the content of this chapter, it is hoped that several crucial steps in machine learning, data collection, data cleaning, feature extraction, model training, model evaluation, deployment, and other links, all have a very clear understanding for common machine learning algorithms. Linear regression decision tree, SVM. Some thoughts on ensemble learning. K-means. These algorithms can all have a better understanding. That's okay, especially the relatively important gradient descent algorithm. This is something everyone should pay special attention to. Remember, because there will also be a deeper level of application in this part of deep learning. So that's a key content of this chapter. Now let's look at 2 thinking questions. The first question is, which of the following algorithms does not belong to supervised learning? I believe everyone should be able to answer this after studying it. Very simple. It is the answer D, because K-means belongs to an unsupervised machine algorithm. So the second question is a true or false question. Gradient descent iterative method is the only approach for machine learning algorithms. I believe the only reaction everyone has when they see it should be that it's a mistake. Gradient descent iterative method is one of the optimization methods in machine learning. There are many other optimization methods, such as Newton's method, that can accomplish the same task. However, the one we commonly use is gradient descent method. Finally, I will give you two websites. You can search and learn more about machine learning on our Huawei Learning website and Huawei Support Case Library. Okay, that's all the content of our second chapter. Thank you all. Good.